Started recording again, and we are sharing. Right, okay guys, let's get back. Let's carry on with semaphores. Semaphores are so good to the point that they started expanding the idea of the critical section and see if can be used for other purposes as well. And they found that yes, there are, when you have multiple processes, multiple programs executing simultaneously on a computer, which you can have multiple threads, and they can pass information to one another or take information. So, similar to processes in a factory. For example, in manufacturing, most of the time, the actual manufacturing operation consists of a number of steps or processes, one after the other. So there'll be a number of machines in a factory. One will do a job and pass its product to the next one as an input to the next machine. And it does, the next machine takes input, performs something addition, some extra work, and passes it as its output as an input to the one machine after it. Similarly, in processing, in computing, they found that when you're running threads, now you can actually have a process that does something, let's say generates random numbers and hands them over to another process that does something else with them, or puts them passing them as in, puts them in an array, and the other one can take them from the array, one at a time. So just like, again, in a factory where a product is created and it's put in a storage space, and then storage space is taken, we take the product from this storage space, put onto trucks that take it away to other locations. So that's, thinking of that problem happens in computing as well, when we are running multiple processes. And they started talking about it in the sense that we need to synchronize those processes in order to work correctly. The same as processes or machines working in a factory. They need to be synchronized. Maybe one is supplying some product or some liquid, the other one takes it and does something with it. But what if the liquid isn't taken, or there isn't? Maybe the tank where one should take for the product from is empty. Does it affect the operation? Sometimes in factories, yes, it does affect the operation. In computing, it does. If, for example, if you create an array, if you're writing a program, say create an array of 10 items, and you start filling into the array location 0, index 0, 1, 2, 3 to 9, and then if you go to the next one, you have a problem. You get an error. So the array was full. You should have checked it maybe if it was full or not beforehand. So we're thinking now semaphores can help in those situations. Synchronize those processes. For example, I'm filling in numbers into an array, and I have another process that takes those numbers from the array. Me installing or putting the numbers in the array, I should check first, or there should be some semaphore that tell me, no, the array is full, don't go in there now. Don't create another number, or don't put the number in there. And with the process that's taken the numbers, if there's nothing to take, then there should be a semaphore saying, no, hold on, the place is empty, don't go and take anything. If you do, you'll have an error. Maybe the program will be terminated or something like that. So now we use semaphores to control those two processes, or more than controlling, synchronize them. So one will keep on filling into the array, the other one is taken from the array continuously. But sometimes the producer is a little bit faster, and we have to stop it every now and again when the storage is full. Or sometimes the consumer that takes from the array is faster than the producer, and will keep taking stuff from the array until it's absolutely empty. And then we say, no, you can't take any more, slow down. So this is the idea of a buffer. Normally a buffer should ideally be always half full. Let's say there's a process that keeps putting stuff in there, and there's a process that keeps taking stuff from there. we call them producer-consumer. So if the consumer is slow and the producer is really fast, they'll fill the place and then they will start having overflows or other forms of problem. So we need a semaphore to stop a producer putting any more stuff if the buffer is full. We just say we wait until the consumer takes some stuff. And if the consumer is the one that takes a lot of data faster than the consumer can produce, then sometimes it gets to a point where there's nothing to take. And if you try to take something from an empty space or an array, it can cause a problem. So this is what semaphores are used for. Think of another thing again. In a factory, you get those guys, the forklift drivers, that take the product that's manufactured and put it into the storage space. And then we have another guy on the other side, so the factory is on this side, so through this door comes all the new products are stored here. But through that door, another forklift that comes in takes them and puts them onto the trucks that distribute them. So we have this little problem. This storage is like a critical section. Sometimes it fills up too much that this guy has no space to put in. And sometimes it's so empty that that guy comes in from the other side and there's nothing to take. And sometimes the two forklifts go in together at the same time and they crash. So we have multiple problems and we need a semaphore for each one of those problems. So in this case, we have two problems. Is the place full or empty? And it can serve both of them. So if we can have a flag that say the place is full, that means you who wants to put more stuff, you cannot go in there. Wait until some is taken away. And if the semaphore says the place is empty, absolutely empty, there's nothing in, that means the guy who wants to take stuff should not come in because there's nothing to take. But the guy who wants to lodge in or put stuff in, they can come in. So that's the simpler idea. Is the place full or empty? And based on that, who can go in? The producer can go in and put in there, or the consumer come and take material from there. But we add a complexity to it that the two of them cannot go in together. We used to have them, for example, in the factory, they both go in, the two forklifts, but they don't even look as they're driving. They just go so fast and twist, and even the doors, they just swing doors. They can't just come banging through the doors and the doors open, or like curtains, they just open and the forklifts go in. But sometimes the other forklift is there and they end up crashing. So we issued another rule, only one of you should go in. So that's another semaphore with one, that only this space, only one forklift. So the guy coming in has to make two checks. Anybody who comes in from either side, two checks. First, if I have stuff I want to put it in this space, I first make sure it's not full. Is it full or is it empty? If it's full, then I'll wait. Because there's nowhere to put, there's no space. Until the other guy comes and removes some space, and I go sleep, and that guy will ring me or will signal me. Okay, see the idea of the semaphore? How it works? So one signal that controls me not going in if the place is absolutely full. But let's say I checked it. Is the place full? No, it's not full. I can go in and put the stuff. But hold on, there's another check. Is the other guy in there? Is there somebody else? Is the other guy with the forklift inside? If they are, then I'll wait until they leave. All right, so there are two checks now to do. Whether I'm the producer, I have stuff to put in the storage. First, I check that the storage is not absolutely full to the rim. So there's a semaphore to check it. And if it's not full, that means I can go in. But before I go in, I do the other check. Is the other guy in there? I want just mutual exclusion. I want to be the only user in that place. You're not allowed to have two users. So that's what it looks like, guys. So these guys, somebody comes in, can be the producer that leaves the stuff in, or the other guy who comes and takes it out. But they're so fast, they're really dangerous at driving, and they just zoom in, and most of the time they can't see where they're going. They can't see if the other guy is on the other side, and they end up crashing. So we put that second semaphore. Only one of you goes in. So this is how you could do it in a code. Say the producer code, for example. Come in, you have data to put into the storage. Well, first, check is the storage empty and it's not full. If it's empty, you can go in, of course. If you want to put stuff in, and if that place is full, then you cannot go in. You have to wait until it's empty. So there's a flag here, 0 or 1, for example. It's a semaphore. So if it's 0, it probably means it's full, and whatever it is. So we just forget that. Is it empty or full? So if it's empty, I can go in. If it's full, I have to wait. Let's say I waited. I go to sleep here. Who's going to wake me up? The other guy, my friend on the other side who comes and takes stuff. So he's already in there. Is the place full? No, it's not full. So he go in. He said, anybody in there? Of course, I'm waiting outside. I'm not in there. So he's going to be allowed in. So he takes data. He takes whatever it is, a box from the storage, and walk out. But while walking out, he'll issue this signal saying, listen, if there's somebody waiting, because I am in, I'm out. That's I'm not in the store anymore. So but I wasn't waiting on that. I was waiting because the store was absolutely full. But this guy just after taking something out of it, so it's no longer full, so it's going to signal me with that V function. So somebody's waiting by the P function. Remember, the P function is check. You either wait or you continue. I'm waiting. But who's going to let you go? The other V, whoever is leaving. Remember with the hotel, if you come to a hotel and the hotel is full, you're going to wait. Who's going to give you the key and get you to go into the room? Is the guy who's in the room. When they leave, they check, are you waiting? Here's a signal. And they wake you up with that signal. So here, in this case, we have two semaphores. One is called empty and full, and one is the mutex, or three semaphores, but we can, for example, the mutex. Let's say I'm the producer. I want to put some stuff in the storage. Is it empty? Yes, it is. It's not full. So I will not be blocked here. I go in, but I have to check another check. Mutex. That means, is the place mutually exclusive? Is there nobody in there? I just want to be in there myself, no one else. If the other guy is in, then I will be blocked. If I'm blocked because the other guy is in, when they come out, they V me with this, or they signal me when they leave. So when they leave, they issue a signal, I'm asleep, I'll be awakened, that means I'm no longer, the place is free, I can go in. And when I go out, I'll issue two signals. If anybody waiting, if this guy wants to go in while I'm in, they want to come in and take some stuff while I was inside, well then I'll know and I'll signal them. I'll look at the queue, is anybody waiting? Yes, we'll send them the signal. If not, just keep going. And is somebody's waiting because the place, they'll say the consumer came to take some stuff out. And they're told, sorry, there's nothing in there. So they get blocked here. Now I tell them, I'm just after leaving something in there. Go ahead. So there'll be signals. So this way, semaphores are used to make processes synchronize together. That's they call synchronization of processes. Or, kind of 2 or 3 processes can work in sync together. That means we'll never go, for example, those two the examples we had, that we will not go into the same space because we are protected by this semaphore. We call it mutex. That means only one user can use it. Mutual exclusion. Mutex means mutual exclusion. That means only one user go in. So if the user is in, then this one gets blocked. If there's nobody in, this guy will go in, but anybody else will be blocked coming in. And if somebody is waiting because you are in, how are they going to get to continue? When you come out, you issue the V function. You say, anybody waiting on me because I was inside the store, now I'm out. You can go ahead. There's nobody in the store now. It's just like, is the place empty or full? Not empty or full, but is there a user in there or there's no user? When you leave, this is just like the toilet idea again, but this is using semaphores. If you come into the toilet or the critical section and there's nobody in there, you just go in there and, make sure it says it's busy. And basically, you're taking the key. But if somebody is waiting, you signal them. You say, it's your turn to go in. Here's another way of looking at it. So anytime there's a semaphore, you get blocked. If you get blocked, you're going to be released by another user that uses the same semaphore when they leave. And when they leave, they always issue the V function. So these V functions will release anybody blocked at the door. Just like the hotel rooms. If you go to a hotel, the example we had earlier, and the hotel is full, you're gonna sleep waiting. Nobody's gonna get you to get moving except the person who is now occupying the room. When they leave, they check, somebody is waiting, they give you the key and they give you a signal to go and use it. This is exactly the same idea, but applying it to other processes and applying a number of them. You can have 2 or 3 or 4 semaphores controlling the operations in a factory or in programming. So that's really the main idea. That's it. They apply it to problems. They call them producer-consumer problems or readers-writers problems. In computing, you can have an array. You keep writing into it. That's the writers, and the readers take from it. But the readers cannot read if there's nothing there. The writers cannot write if it's full and the reader is slow. So we have those semaphores that control the operation. That's it. But once you understand the overall concept, the operation of it, then maybe you can, they all have the same logic to explain it. It's just basically follows the same logic. Whether a place is mutually exclusive, that means should only be one user in it or X number of users. Of course, we can use semaphore for one user. We can also use semaphore. The advantage of semaphore, it works for any number. For if the critical section has one user or multiple users. So that ends our kind of talk about process synchronization. That's using 3 techniques, locking techniques basically to protect certain areas of the code that can, if it's executed by more than one process, it can cause a problem. So 3 techniques were developed. One is called set and test, test and set, and the other one is wait and signal, and the last one, and the most up-to-date one, is the semaphore. You need to understand the 3 of them, which one is better, what's wrong with, say, the first technique, and then what's wrong with the second technique, and that's what's the advantage of the semaphore. So just 3 questions while we're at it. Test and set. Who can tell me, very basic idea, how does the test and set mechanism that's used for protecting a critical section? Anybody want to have a go? It's casual, not, you don't have to speak scientifically, but just show us that you know the idea. The first one, they call the test and set. Come on, have a go.
Just to check, so critical section is easier for
Okay, so there's a variable. What does that variable indicate? It uses a signal or a flag or a variable, usually 0 or 1, or free or busy, or red and green. So that's important in the test and set. All right, and somebody approaching, what would they do? Come into a critical section using the test and set.
It's not allowed to run the 2 codes the same line of the code because probably you could be conflict inside of the
Okay, how do you know? How does it work? We have a signal that says, say 0. What does it mean?
Zero is not allowed to meet.
No, that's in the semaphore. In the test and set, 0 is free. The critical section is free. So just from the name, guys, test and set. Anybody approaching, they must test this flag. Is it 0 or 1? You need to look at it and find out. If it's 0, that means it's the critical section is free. Set it to 1, you set it busy, and you go in. Like a critical section, like a toilet. You go in, you check it. If it's free, then you can use it. You turn it, close it, or turn it to set, lock it, and go in. Right? And when you leave, you need to say, you just unlock it and put it back to 0, indicating it's free. What's wrong with this technique? What's wrong with this technique, test and set? Yeah?
Busy wait and starvation.
It can suffer from starvation or busy wait. So you should understand how does starvation happen, because You're testing and checking and then go to sleep for a little while. Check it again, sleep for a little while. If you check it and you went for sleep and now it became free, somebody else comes in, checks it while you're asleep, they can go in. And if this keeps happening, then that's how you could actually be left in a starvation situation. You're basically missing your turn. And the reason there is no queue, you're just waiting, like an airplane. You just wait. There's no specific place where you say, okay, you wait here for the toilet use. No, you can. Some people sit down in the nearest seat. Some people go near the window. Some people start chatting the stewards or the air hostesses, and then they forget about the toilet and they start missing their turn. So that's how you could miss your turn, because you're not constantly checking it. But the busy wait, because you are checking it all the time, that's another disadvantage. All right, wait and signal. What do we start the variable with? The second technique that solves the busy wait, and it solves the other problem. But I can't remember what the other problem is. Okay, so how do we solve the busy, not the busy wait, the missing the turn? How do we solve starvation in the next technique? Yeah? No, go on. Yeah, so waiting has to be in a queue. A queue was introduced. So anybody waiting, they must join the queue, because the queue, we know where you're waiting and who is next. So that solves the problem of starvation. How do we solve the problem? How did we solve the problem of busy wait? Oh, not busy wait. Yeah, the busy wait problem. How is it sorted out? How did we remove the busy wait situation?
That instead of constantly checking the flag, we send a signal, and if there's anybody in the queue, they will.
Yeah. So it's no longer your own personal responsibility to keep checking if the place is free. You just go to sleep, and whoever is in the place now has the in the critical section has the responsibility when they come out to signal you if you're the first person in the queue. And if there's nobody in the queue, then they'll leave the key or the. All right. What's the initial value for a semaphore? When we start a semaphore, what do we put that S value to?
Maximum number of possible processes.
The maximum number of processes allowed into the critical section. If you're allowed 3, then that's what we must start with. What about the initial value of S if we are doing the wait and signal? What's the initial value we start with? Yeah, 0. 0 means that the critical section is free. Okay, guys, that's well done. Please be ready for the test next week.